All right, my wonderful students, welcome. This is the beginning of the last week of Summer B. And on Thursday, we'll have a cumulative final exam. And I'll just take a moment to say right now that I've enjoyed working with you guys. Almost everybody in here. The only ones that I haven't enjoyed working with are the people that aren't actually here. So how could I? But seriously, it's been a lot of fun, even though it's been a lot of work. It has been a lot of work. And just the mental work, and you guys have done pretty good. We got one more week to go. Let's talk about this and that, about exam 3 and so forth. Then we'll get down to brass tacks with diffraction and stuff. About exam 3, first of all, we're still waiting for the scantrons to be graded. So you never know with those guys over there in test scoring. Sometimes they're really fast. You know, you bring them in at, well, for us, it's always going to be after after hours because we finish at 5. But, you know, a lot of times I'll finish, you know, the noon class at 1:30 and get them over there about 1:45 and they're done by 3. That's during the regular semester. So it's kind of hard to tell. But anyways, hopefully this afternoon sometime while we're discussing diffraction, those grades will get posted. Written homework will be ready tomorrow. A few of you asked for homework from previous homework assignments, and I actually have homework 4 here from last week, and actually I have a bunch of stray papers, Bruno, Barusco, et al. For homework 1, 2, and 3 as well. So you can grab those after class or during the break. That being the case, as I told you that we would do a full-scale grading example today in lecture, and I want to do that, but the data's not ready yet. You know, the exams aren't in. I want to show you how to put it all together. You know, best 2 out of 3 and all the homework in and stuff. And so when we have, and I want to do it with live ammo. I want to do it with real data. And so, you know, the data's not completely in yet. So hopefully by tomorrow we'll be able to do that. Any questions about any of that business? Okay, let's keep going. This week we're going to start off today, chapter 27. And we're going to talk about sections 1 and 2 about Young's experiment, the double slit experiment. And then we're going to blaze up to section 5 and talk about diffraction, the single slit diffraction. We're going to work some examples for both. And from the second set of examples of diffraction, chapter 27:5, I'll introduce you to the idea of using diffraction measurements and observations as a means to measure the unseen, the unseeable, atoms, molecules, crystals. We'll be able to do that. We'll make sense of how scientists have done that for the past several decades using diffraction techniques for electrons and X-rays. We'll talk about X-rays primarily. And then tomorrow we'll talk about chapter 29:3, photon energy. A couple other things from chapter 29, the de Broglie hypothesis, and also where the de Broglie hypothesis is mentioned in chapter 30. We'll also talk about X-rays in chapter 30, section 7, and then, whoops, wrong way. Go through this again. And then we'll talk about radioactivity over there in chapter 31. And we'll just go over some of the basic decay modes of radioactivity. And actually, 31-6, you should be able to read through that pretty well because it has to do with half-life and radioactive decay, exponential decay, which we've already talked about in the context of capacitors. And it also applies in the area of radioactivity. So that's our basic outline. And hopefully we'll do that Monday, today, Tuesday, tomorrow, and a little bit Wednesday. And if we have some extra time, an extra 30 minutes or so on Wednesday, we will do a little review. I'll prepare a little review in class that I'll hand out. Maybe 10 or 20 questions, kind of like a test, but you'll be able to use your iClickers to do it and study with each other and, work on stuff. And then you'll click it in as if you're doing it on, self-paced mode. And I'll convert that into some bonus points as well. Now, something's not on the outline, and I'll just mention it now. Homework 27... Chapter 27 homework, I think it's chapter 27 workout, it's called. Raise your hand if you got that done over the weekend. Okay, good. Oh, I see a few of you didn't. Okay, because we're doing our teaching on chapter 27 right now. So what I'll do, I'm not going to reopen the 2 attempts that are up, but what I'll do after class is set up a 3rd attempt, okay, on that chapter 27 homework. And so that you guys have done it already, you're good. And if you haven't done it, you get another shot tonight, but you only get one. So hopefully that'll go good. The mega review is activated, and that will be converted to 3 or 4 bonus points maybe, okay? So that if you guys are trying to get your grade over the borderline, hey, I have a question. When are you guys doing labs this week? Oh, so when do you finish Wednesday? Well, okay, let me ask you this. Raise your hand if you're finishing Thursday. Oh my goodness. We got a big disaster. That means I won't be getting your grades until after Thursday. So I won't be able to chat with you about your grades. But you guys know how to handle it. Just, multiply your percentage in lab by 60 and then add that into your pile of points. Round up. And that'll be good. What else was I going to say? Oh, office hours Wednesday, as always. And that'll be a good time for office hours. 12:30-ish to 2:30-ish, room 158 in the Physical Sciences building. And a good timing to get you ready for the final. By the way, the final is going to be cumulative, and I have an announcement. No, I have a discussion post. I have a discussion post in discussions that that kind of lays out the basic structure. And so approximately it's going to be about 36 or 37 questions of everything prior to today, from the first day of class up until last Thursday. Okay? So that's And then there'll be about 13 or 14 questions about stuff we talk about this week, today. And that's roughly, this week is roughly half the amount of time we had between the previous midterms, so it's about right. So you'll have 12, 13 questions, maybe 14 on stuff that we talk about this week, diffraction and so forth, and particles and radioactivity. And then the rest will be, so it's cumulative all the way back to day one. And there will be a little bit of Bernoulli activity on the final. So be ready. As we used to say, expect the unexpected. Be ready to think on your feet and let the chips fall where they may. And I know a lot of you guys are trying to crush the final, and I hope you do. But it won't be easy. It'll be possible, but it won't be easy. Steffi, I got your unit down here. If you care to step forward. So that's the scoop on that stuff. All right, now I have a clicker question for you. Go ahead and answer this clicker question. It's basically kind of a survey question, so just answer the one that makes sense to you.
Thank you.
And let me give you the question. So just answer whichever one is true for you. Good. Ten seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, you have to hit the send key, so make sure you hit send. Make sure we get a few. All right, we've got a few more. Okay, good. I'm actually kind of curious to see what you guys answered. Let me click this closed. Wow. Nobody answered B? Smartphone? Seriously? You can't use it on your... Some people did. They answer.
I like the downloadable e-text one, so I don't know if I can do it through Vital Source, which is what that is. Vital Source opens on your phone, but I don't know if it does it through web courses, so we have tried it.
Yeah. All right. All right. So this is good. Thank you for clicking that. I'll show you what the results are. So everybody that answered gets a point. All right. Let's switch back to the regular lecture. Thank you for doing that. I want to talk about the double slit experiment now. And as I mentioned last week, the double slit experiment is basically the foundational example of all quantum mechanics. Every quantum mechanics student on the planet tackles this problem. Now, we're tackling it from the standpoint of light waves. In quantum mechanics, you tackle it from the point of de Broglie waves, which we'll talk about. If you have light waves that pass through a given point, the electric fields combine, the principle of linear superposition. Now, I'll make a note, those of you that have the bookshelf app already know, or possibly already know, there is something called nonlinear superposition. So make a note. A famous example of nonlinear superposition, nonlinear systems, is turbulence. Turbulence, turbulent fluid flow. Very difficult. It's nonlinear. With an electric field, you just add up how many constituent fields you have. It's just like a net force. No matter how many forces are acting, you just add them up vectorially. Maybe you have to use some Pythagorean theorem and whatnot, but you add them up. And then that's the net force, or the net electric field, or the net potential. But in turbulent flow, it's a little trickier. And here's the interesting thing about turbulence. We don't know how to handle it. We don't have it solved. It's not just difficult. We don't have anything solved. We haven't got any solutions to turbulence. We've got approximations. We've got good models. But we don't have a tight F equals MA type solution. But people are working on it all the time. Now, this one, so this is linear superposition. And let me get my cursor over here. Come on, cursor, where are you at here? Here we go. All right, so here's your source 1 up here, and here's your source 2. It's a diagram from your textbook, chapter 27. I think this is the very first one, in fact. And if there are two different sources from two different locations, then the waves that spread out in all directions, not just these two, but this is just localizing two waves. If they arrive at some point and they're both in phase, peak to peak, and here's the side view over here, peak to peak, trough to trough, then you'll get maximum amplitude oscillation. So that's this big blue squiggle over here. Now the way to think about that in the ocean is, if you ever listen to Discovery Channel or the History Channel or anything like that, you'll see, when they're not showing shows about aliens and stuff, a lot of times I'm not joking around, they have the shows about the ghost ships of the Atlantic, the Bermuda Triangle and all that stuff. And one of the things that they talk about is rogue waves. And rogue waves are real. We filmed them. And a rogue wave is basically, you have a storm off the coast of West Africa, and you have another storm off the coast of Nova Scotia, and they're sending waves across the Atlantic. And some of them end up here at Cocoa Beach, and you go swimming, and you surf on them. But, out in the middle of the Atlantic, where the shipping is and stuff, two waves combine, peak to peak, trough to trough, like this, you get a rogue wave. Big, huge wave, 40 feet or more, that can dump a big container ship or a tanker or a freighter, of course, smaller ships. And so, if you look on, what you got to do? If you look on YouTube and you write in rogue wave, you'll see some really excellent and actually kind of scary, if you think about it, videos of rogue waves out in the ocean. So two different sources. So here's Nova Scotia up here. Here's the coast of West Africa, Cape Verde Islands over here. And so here's some guy out here in a boat, and he's getting rogue waves. Here's the rogue wave down here, side view. Now the same thing happens with the electric field. The electric field, the peak of the electric field, formed by a dipole antenna, the electric field is up and down, and the magnetic field is forward and back like this, so the propagation is E cross B direction. So this one could, that blue curve would be a nice representation of the electric field at various points, and they're moving. And the position P is such that if your sources are not moving and you stay at point P, you're going to get a good strong radio signal or a good strong light signal at that point. Now, if you step half a wavelength away from there, you're going to possibly be out of phase. But at that particular point, you know, you're going to be getting a big tall crest, a big deep trough, and then, you know, neutral water in between. And then another big crest, double high, double deep trough, and in between the neutral point, you know, sea level. Right? It oscillates above and below sea level. Same thing with electric field. Now the principle is down here expressed in a mathematical formula. L2 minus L1. Here's L2. That's the distance from source 2 out to my point. So that's the length of this kind of rectangle here, seen in perspective. And here's another rectangle up here, L1. And if the difference between them is either 0, if it's 0, then they have the same distance. Okay, the same distance from both sources. But if it's one wavelength, m equals 1, you get constructive interference. Okay? And that's what this big rogue wave squiggle over here signifies. So there's your maximum amplitude combination signal. They're superposed. Both of these two blue, the smaller blue waves, they're in sync, they're in step, they're coherent, they're in phase, and therefore the amplitudes add up together. And you get something called constructive interference. And so if you're at point P in a rowboat, you're going, whoa, you're way up here on the top of the crest, and then boop, you're down here at the bottom of a trough, and you're looking up at water, walls of water to left and right. Not a very comfortable feeling. And similar for the electric field. At that point, an electron will be on a joyride up and down in response to the electric field, whereas a slight half a wavelength away, bing, your electron's just kind of sitting there. And that's this next diagram. This one gives you the basic lowdown for destructive interference. Now, take a look at the side view first, over here, in this kind of oval side view. Okay, the top one from source 1 and the bottom one here, excuse me, from source 2, they're out of phase by 180 degrees. And so what that means is, no matter, you know, at point P, if source 1 gives you a peak, source 2 is giving you a trough. All right? So if you're out in the ocean, you're sitting pretty. It looks like calm water. And everywhere around you is looking pretty rough. Okay? If you've ever been in a canoe up in Canada or up in Maine in the wilderness, or out in the Rocky Mountains in the rapids, they have these things called haystacks. And up in Canada, where some of the big rivers empty into these big lakes, they have just enormous areas of rapids, and they have standing waves. And you canoe through them, and they're just like, they look like haystacks, but they're made of water, they're standing waves, and they're ferocious. But if you go through them the proper way, you go through on flat water, you're okay. And that's what this is. So this is peak to trough, trough to peak. And that will happen when you have a half of a wavelength extra. Okay? So an integer plus a half. So 1/2 for m equals 0, 1.5 for m equals 1, 2.5 for m equals 2. Or you could go like this, 1/2, 3/2, 5/2. You know, odd integer halves of the wavelength. And bang, if that's your path difference, L2 minus L1, or L1 minus L2 if you're looking on the other side. You know, if you're looking down over here, you know, down where this caption is, you know, it might be, it's closer to source 1, or it's closer to source 2 than source 1. So you'd look at L2 minus L1 over, or L1 minus L2 over here. But anyways, no matter what, if you get this exact kind of a distance difference at your point, then you have flat water, or what we call destructive interference. And that applies for the electric field and magnetic field too. All right, so it's easier for us to visualize this as describing the electric field. Now, what that means is that if you have a double slit and you beam light through it, if you look at a certain angle, and you're standing behind it, so you got this waves, and going through these slits in your device, and then it's projected onto a wall, and you're able to look at the wall. In some areas of the wall, it's going to be bright. You're going to get constructive interference. In other areas, it's going to be dark or not as bright. That's going to be destructive interference. And that's what we call a diffraction pattern or an interference pattern. And the textbook uses the word fringes, but I do not like the word fringes for those. But that's what the textbook uses. All right, so here's the scoop. And here's the basic idea here. Okay, so if these two sources are always in step, so electromagnetically, if they're powered by the same current, for instance, and the same voltage source, a sinusoidally varying voltage source, then you'll get waves out here and a whole variety of positions where you have maximum amplitude, you have the rogue waves. And then at other positions, you'll have flat water, and the field will be null at that point, permanently null at that point. Unless something changes with the source, you bump the source or you move the source or something like that. Now here's another way to look at it. Here are the two slits. Okay, so this is the actual diagram that every quantum mechanics course starts with. But for us, we're just thinking about the diffraction of light for today. So here's S1. Every little opening in this barrier is considered to be a tiny source. So the light waves come in from the left side here, and they come in as plane waves. If your lamp is far over here to the left, like over by the wall, then by the time it gets to those slits, they're going to be pretty much plane waves. They're going to be marching through, two flat pieces of plywood just marching through. If that's the case, these things will be in phase. Okay, and the way that we figure out the physics of this, we consider this point here at S1 in the gap, we consider that point to be a source of spherical waves. In other words, like rings, when you drop a stone in a pond or in a swimming pool and the waves go out like rings, if everything's flat. Okay, the rings go out from this point right here in the gap and then down from this one in the gap. And then every ring, the distance from the peak to peak between the two rings is one wavelength. Let me repeat that. You're in a swimming pool, you're on the side of a pond, you drop a pebble in, and the rings form, and from the top of one ring to the top of the next ring on the way out, or trough to trough, either way. Trough to trough, peak to peak, is one wavelength. All right? And so now you've got two sets of them. So you'll have rings coming half, and actually semicircles. So if you're going to draw in the wavefronts here, boy, this is a boring topic. It's a lovely day. Yeah, but that was 4 days ago. Oh, the final, yeah, okay. All right, that's good. That's a good excuse. Anyway, so if you were drawing the wave fronts, we would call, and what the technical word for this phenomena is wavelets. We consider the electromagnetic waves, they come in as plane waves, they hit this gap S1 and this one down here S2, they form wavelets that come through the gap as if there's somebody dipping a stone into the water at the same frequency as the light waves are coming in to the gap. All right, and then on the other side of the gap, on the right side of the gap, they form semicircles. And the distance between each, so go ahead and draw in some semicircles around each gap and try to make them the same distance apart. A bunch of semicircles over here around this guy, and a bunch of semicircles over here around S2. All right? Now, right down the middle, you got your central image. Okay? So this is a bright fringe. All right? Because the distance from S, if everything's symmetric, so you put this dotted line right down the pipe, okay? And so little Pythagorean theorem, L1 is equal to L2. If this distance up here above the dotted line is equal to this distance down here, and then they share this dotted line distance, ding, L1 and L2 are the same size. So you're always getting, at that point, you're always getting constructive interference. So your first rogue wave and your biggest rogue wave is going to be here because it's closer than anywhere else to these two sources. Right now, if you go up here a little bit up above that, okay, so your center line's right through here, but if you go a little bit above that, okay, now the difference is this little line segment right here between this dashed line that goes from S2 down to this blue line. So from S2 to this point, the bright fringe, the first, this is M equals 1, bright fringe up here. L2 is bigger, L1 is smaller, and the difference is 1 lambda. So this is M equals 1. Constructive interference right here, all right? Now, if you don't go quite that far above the center line, you get a dark fringe, all right? So you get the central, so here's your brightest one. And then above that is a dark fringe where you get some destructive interference. All right, so again, you have this little slivery right triangle down here, and that little right triangle is pretty important. Okay, and we're going to do some trig out the wazoo. Actually, it's going to be, I shouldn't say it's trig out the wazoo, but we're going to do a lot of trig. It's just really simple trig. It's a right triangle. But anyways, this right triangle here is everything. Okay, so if this little sliver of extra distance here is half a wavelength, bing, you have destructive interference at that point. Okay, so the dark fringe comes first, then a little bit above that is a bright one. And then you'll get bright, dark, as you go up above the center point. And then you'll, similarly, down below here, below the center point, you'll get bright, dark as well. And if everything is symmetric and everything's parallel or right angle, you get nice looking fringes that look a little bit like this. All right, so here's the central image right here, the 0th order. Okay, so this number up here is 1. So M equals 1, here's the first bright fringe away from the center. And here's the other one. M equals 1 left, M equals 1 right over here. Right? If it's symmetric. You know, the light, those wavelets, Diamante, come out. They come out symmetrically. So what you get on the left is what you get on the right. All right? And so you can see it here. It's pretty, unless somebody bumps your apparatus, it's going to look something like this. And this is the brightest one here in the middle. M equals 0 is usually brightest. And guess what, you guys? This distance, if you measure this, this is an image on the wall. This is what the wall would look like, or a projector screen. And if you do this on the wall, you measure the distance between two dark fringes, or between the central and the central image, or the central fringe and a dark fringe, or two dark fringes or two bright fringes. You measure that, you can actually figure out the wavelength of the light if you know how far apart the slits are, and vice versa. If you know if you use a red helium laser, then of a set wavelength and a set frequency, you can figure out the size of any gap or any pair of gaps that you feel like. All right, so here's kind of an idealized view. Now the idea, this is the same thing. And what we're doing is we're focusing on this reddish pinkish triangle here, this right triangle. That triangle is everything. All right. Now here's the approximation that you're working with over here. If the screen is relatively far away, many multiples of the separation of the slits. So D here, little d is the separation between slit 1 and slit 2. Okay. So if that's like 1 nanometer, and the distance all the way out here to the screen on the right is like 20 centimeters, and that's a whole lot of nanometers, then you're going to get a good approximation that this blue line and this blue line over here in the left image, A, they're going to be parallel. Because they're parallel, you can use right angles here. And the difference in the distance between source 1 and source 2 out here to one of the bright spots or one of the dark spots is delta L. And you can use the wavelength and the separation D to do a little bit of trig. So this sharp acute angle here, the small slivery acute angle, is theta. All right? And that's the same as this upward and downward tilt angle, theta. Now this one over here in this right side diagram, this theta here is your look angle. That's the angle that you got to, instead of looking straight at the central fringe, you got to tilt your eyes, 7 degrees left or 7 degrees right. And you'll see m equals 2. That's what they've got. They've got the m equals 2 bright fringe up here, okay, at this viewing angle theta. Now that's the same. I have to let that go to voicemail. Turn off the ringer. So if the distance is far relative to the slit size and the wavelength size, these lines will be parallel. That gives you a right triangle to work with. Your delta L, the path length difference, is either going to be, theta for the bright fringes are going to be an integer times lambda over d. Because d is if you look at this right triangle, draw a big picture of it. We're going to draw some pictures here in a minute when we go to the document camera, but the hypotenuse is d. Now, hopefully, you've designed your two slits at a precise distance apart. And then you can measure wavelength. Right? Because then you measure theta from your aim point over here. Here's theta. All right? You look, you get it all set up in the lab, and you get everything square and whatnot and level. And then you go over here, you measure this. So my second, this is m equals 2. And my tilt angle here, theta, is 7.3 degrees. Okay, sine of that, and then m equals 2, and then d I know, so I can get lambda. So you can actually measure the wavelength, and students, you can measure the wavelength in nanometers of like a red helium neon laser, just like that. In this class, you could do it in lab. I don't think you're going to do it this week, but they should. And they should have a diffraction lab. Now, the same point is slightly different for the dark fringes. So here, this diagram is sighting in on m equals 2 and m equals 2 down here, above and below the central bright fringe. But, if you want to measure, here's the first right here between 0 and 1. Here's the first dark fringe, and here's the second dark fringe. And, so maybe you get the sharpest dark fringe down here at m equals 3. Okay, measure it. And you just put in a 3 up here, and then 3 plus 1/2, so that's 7/2. And then get D. You know what D is because you built the device, and you just measured theta, so you can still figure out lambda. Right? So you have your choice of what you want to do. Now here's the interesting thing about quantum mechanics. This is for light waves. And de Broglie's hypothesis, as we'll talk about this week, was electrons and protons also behave like waves. Nobody had ever thought of that before, but it all works out perfectly. The hydrogen atom was explained very, very well with de Broglie's hypothesis. And so we can get electrons to do this as well as light. So we get X-rays to do this. You beam a set of X-rays through a double slit, bing. You can measure the X-rays or you can measure the distance, either way. If you know the X-ray wavelength, you can measure any distance, right? And same thing, we do it with electrons too. Sometimes we use electrons and protons. But a lot of times we use light, visible light, stuff like that. All right, let's go to the document cam. Let me pause the YouTube for just a second. Let me get my cursor over here. Okay, so what we just did was the single slit diffraction pattern and measurement. So make a note. This is really of use to us because it allows us to make measurements of things that we cannot see. All right? And here's a little blurb from the chapter concerning Huygens Principle. Every point between the openings, or every point in the gap is considered a source of wavelets. They move forward at the same speed. They form. So here I mentioned the rings. Get my cursor over here. Okay, so I mentioned the rings going outward. You drop a stone in a pond or a lake, and the rings go outward. But we only use semicircles here. So here, these red ones, those are red semicircles. And this first semicircle is going out from number 1. The second semicircle you see here is going out from number 2, from number 3, 4, and 5. And they use 5 wavelet sources. Really, they're infinitesimally small, so you can't really measure them, or count them. But it's okay to use them in this way because they are symmetric above the center and below it. And you can see the plane wave front. Okay, here it is. And this is for sound waves. It's in chapter 29, or chapter 27, but it applies to light waves as well. Now, here's why it's important. The amount of diffraction that you see through a single slit, first of all, if your wavelength is really tight, like image A over here, you get a little diffraction, but not a whole, you don't have a big searchlight. But over here, whoa, you get a nice searchlight. You get a good dispersion. All right? Now, what this is like saying that when we talk about Huygens Principle, or not Huygens, de Broglie's Principle, tomorrow, that the wavelength and the frequency of a wave corresponds to its momentum and its energy. The tighter the wavelength, the smaller the wavelength, the higher the frequency. The higher the frequency, the higher the energy. Let me repeat that. And this applies to photons and all particles. The smaller the wavelength, the higher the frequency. The higher the frequency, the higher the energy. Because the photon energy is proportional to the frequency of the photon, the frequency of the field. The photon is a quantum of the field. All right, so that's what we're working with here. And so the energy of your photon that diffracts through that opening controls whether you get much diffraction or not. So look at this. What this tells us visually is that high energy photons just go blazing right through. They can't penetrate the barrier, so they stop. The ones that are in the gap, they just blaze right on through. They don't really diffract much. All right? Now the pokey, the low energy photons going through a gap, whoa, they're diverted. That energy gets spread out. It's waves, light waves. All right, now we did the document cam. And here's something that's important, the Rayleigh Criterion. 2-point objects are just resolved when the first dark fringe in the diffraction pattern of one falls directly on the central bright fringe in the diffraction pattern of the other. So here's two BBs, so here are the two objects, two little BBs, a red one and a blue one down here at the bottom, okay? And when the distance apart, that's this angle theta here, is enough so that the first, so here's this first dip is where in the blue image, okay, so here's the first dark fringe. That's where the central bright fringe is for the red image. And when that happens, you can tell them apart. Any closer than that, you can't really say that you're separating them. Okay, that's the Rayleigh Criterion. And so these two, this is a diffraction pattern through a single slit, single opening, circular opening of these two objects. So the light bends around these objects and forms this diffraction pattern. And you would say that these two items are resolved. Now you can read about that. That's actually not in 27.5. I think it's after chapter 27.5. Now, here's our punchline for today. Measuring a diffraction pattern, single slit, diffraction grating, whatever it is, you measure the bright fringes and the dark fringes on the projection screen. That tells you the size, if you want it, of your opening. You guys ready or what? I'm waiting for you. What are you doing over there? Trying to get in med school or not? I'm trying to give you some information here. How do you think people figure out about these advanced drugs and stuff? They look at diffraction patterns. X-ray diffraction, electron diffraction. You know, here's the retinal molecule. We got this thing bagged. This is the molecule that lets you see. Retinal. It's a compound in rhodopsin, which is in the retina of the eye. And when it gets hit by a photon, it bends, it flexes. It goes from cis to trans, and then it relaxes back to cis. And then it gets hit by another photon, bang, it extends again. It's billionths of a second, very fast, because it's really small. How do we know? Because we use diffraction. We figured these babies out. Here's another image. The universe itself. We have buckets. We got buku telescopes looking at, you know what we use? At the universe, we diffraction gratings. And that's why we know that 74% of the visible universe is hydrogen, because we can see the spectral lines of hydrogen, the distinct color that only the distinct set of colors that only hydrogen produces. And so basically, and that's basically because we know how big a hydrogen atom is. The very first guys, 100 years ago, they were figuring it out. Getting the hydrogen atom figured out. It's one of the only atoms that we really know very much about. Well, you see it everywhere.
Quick question.
Here's another one. Yeah, go ahead.
On that previous photo, where was that thing, man? Or where was that observed date?
This one?
Yeah.
That's in South America at a place called Paranal up in the...
Well, now that, like that picture is the Milky Way, right? Because there's so little light pollution that you can actually see the Milky Way, right?
Yeah, it's the Milky. It's not light pollution, baby. That's the Milky Way.
Well, I know, but usually you can't see because of light pollution.
Oh yeah, here in Orlando, yeah, it's hard to see. Yeah, that's up in the Andes. And here's Mount Etna. Look at that. How do we know that what's in molten lava pouring out of Mount Etna? And how do we know that Mount Etna is different than the volcanoes in Hawaii? We study the chemical composition by using diffraction. Here's another one. How do we know the thermal properties of water? That's water, baby. That's water in the water vapor, water droplets, liquid water. There's probably some hail up in there, so that's frozen water. Solid water. How do we know that? How do we know the crystal structure of water? Diffraction. Oh. How do we get good optics? We design them we figure out the compounds and, the very specific kind of glass that will give us brilliant optics like this. And then, of course, you got to get somebody that surfs pretty good. What is that? That's what we call a Poisson spot. If you put a sphere in the light of a laser, this is a green laser, it should cast a shadow, right? But it doesn't. If you put your camera close enough behind the BB, behind the sphere, where it should be a shadow, nice and dark, because light just goes right past the sphere. If you put your camera up close, you get a bright spot. And this is famous. This is a very famous effect, Poisson spot. The guy named Poisson predicted that if light was really a wave, and matter of fact, he said the light cannot be a wave. Because if it were a wave, we'd see this. So somebody went out and said, okay, I found it. I photographed it. That's back in the 1800s. And they figured it, they found it. So Poisson's spot, he thought he was killing the light theory, the wave theory of light, but he verified it beyond the nth degree. Oh my goodness. Molecules and their interactions. For those of you in Florida, this is something we call snow. And here's something else. Cohesion between water molecules. Now here's, for all of you guys going to med school, you've all seen this. One of the most famous of all X-ray diffraction images. It reveals the double helix structure of DNA. And here's Rosalind Franklin. She's the one that got it. She made that image. Now tomorrow, we're going to talk about photon energy. And this guy, Max Planck. And what he's going to show us, oh, look at all this stuff. Periodic table. Here it comes. A wave equation. F equals MA. E equals HF. Here it comes.
Hey, Dr. D.
There's Max Planck. And Planck's constant. The one constant that rules them all. I'll see you tomorrow. You're dismissed.
So, since it's fully sources, and let any of us keep our